Hi everyone, and welcome to another mini course at Physics Latam. Today we are very happy to have Veronica Pasquarella from CIMIS at Shanghai. She's gonna talk about particle physics, a crash course for mathematicians. Her research focused on homological mirror symmetry and its applications to string theory and Calabi-Yau categories. Veronica completed her PhD in mathematics and theoretical physics at the University of Cambridge last year. Prior to that, she earned a Master of Advanced Studies in the Mathematics Department in Cambridge. She also completed a Master in Theoretical Physics and a Bachelor in Physics at the University of Trieste in Italy, where ICTP is located. Remember to raise your hand at any point if you have any question, and now I leave you with Veronica. Please go ahead.
Okay, thank you very much, Daniel. Thank you, first of all, for inviting me to give these lectures, and it's an honor for me to take part to this activity, which I think is great, to go beyond barriers, distances, and it's great to help in, advancing knowledge in countries, developing countries. So I'm very happy today to start with the first lecture of, as you said, particle physics, a crash course for mathematicians. This is the title of a paper I wrote at the end of my PhD, which was for me an inspiration towards going in more mathematical understandings of the fundamental physics that I was passionate about and I'm still working on. And this paper is quite short. This is the archive code that you will find, and it's basically based on other papers that I had in the previous 2 years and also my PhD thesis. So I'm not going to give any detailed reference in this set of lectures, but if you look at my papers, you will find a very detailed list of other more recent and also well-known literature in these topics, where obviously everything is going to be covered in much more detail than what I could do in 4 lectures. So let's start. So the outline is the following. My lectures are going to be split in between these. So first of all, I'm going to give you some motivations for this work that I'm presenting and the main roadmap that we will follow. Obviously, this is very much on a personal note. You could have the same topic discussed in very different ways, and I'm using tools that I learned during my PhD. So obviously, you could have different approaches for the same thing. I'm going to explain for an audience which is not at all familiar with physics, so apologies if you know already these things, but it's supposed to be pedagogical for this reason. But the second part of my lectures is going to be more advanced. So I'm going to give you details about where the failures of current particle physics are and why I believe that advancements in unification of fundamental laws of nature should come from mathematics if we are looking for an achievement that can be obtained in the short time. So I'm first going to explain what are fields and interactions as the basic building block of particle physics. And then I'm going to introduce amplitudes that are the basic observables in in particle physics and how they are related to Hilbert series, which is more towards the calculations that you would do in algebraic geometry. So we will see calculations of Hilbert series in the second part of these lectures when we will go towards more abstract formulations of what could be quantum field theories that you could obtain, that you could start with to obtain the standard model of particle physics. And then the first part will close with some open questions in quantum field theory. They're not absolutely all of the open questions, but they are those that would, if understood, if answered, they would give certainly groundbreaking advancement in the field. Then the second part of this course is going to be dealing with quantum field theory from category theory. Now, this is basically something that has been developed in the last 3 years, I would say, from the Science collaboration, but it started off from work that was originally made in like the 80s or 90s, starting off from the understanding of two-dimensional rational conformal field theories. and how these could be related to things like Chern-Simons theories, and how Chern-Simons theories has been topological theories that could live in the bulk of one-dimensional lower quantum field theory living at the boundary. So we will see this in much detail. In fact, the second part is most likely going to spread around 1.5 lectures, probably even more. And in this part, I will introduce some fundamental notions in particle physics, such as the partition function and charges, which are essentially basically the essential thing of quantum field theory, because if you know the charges, you already know what are the symmetries involved in the system. And if you know the symmetries, you can write down Lagrangians. And Lagrangians are in turn basic building blocks because they give you the way of defining actions, and from actions you define partition functions. And from partition functions you obtain correlators, and correlators are nothing but the amplitudes that you want to obtain in particle physics, and that you can experimentally test and see if you need to go beyond the standard model. So everything that I said in this minute is just basically going to be spread around the whole lecture, the whole course. So don't worry if you didn't get exactly everything that I said, but we will come back to this in more detail as we go through. So the main thing that I want to stress is that everything that I will be discussing will be with a lens of category theory and maths, rather than a more physics approach that you could have to describe and learn these topics. So then I will introduce the notion of gauge theory as in the mathematical formulation. So we will see this in the language of Fried and Telemann, who were the first to describe it in those means, and the introduction of relative field theories that are a way of like obtaining. So it's the step before getting an effective quantum field theory that you would like to study. So it tells you that you can obtain a certain quantum field theory by studying its symmetries and by choosing what are the boundary conditions of the fields that live in that. So automatically that tells you that you can relate different spectra, different charge spectra in the theory, and different theories together. So also encoded in this chapter is basically the notion of dualities, because dualities play an essential role in particle physics, but also in string theory. So this is another important thing to bear in mind. My whole lecture course is going to be heavily relying on the assumption that particle physics descends from a higher dimensional theory, which is called string theory, which is supposed to be one of the most promising unifying theories of fundamental particle physics. And by assuming that there's a whole plethora of mathematical structures that automatically is needed to be accounted for, such as Calabi-Yau structures and Calabi-Yau categories, and a whole and a landscape of dualities that emerge from those assumptions. So I will be relying heavily on that. So as a consequence, my approach is very much top-bottom. There could be other ways of doing that, doing a bottom-up approach, which would be instead involving starting from the standard model and then obtaining extensions. So to go beyond the standard model and seeing what are the effective field theories that one would actually obtain by adding further particles and interactions. The last part of the course is going to be dealing with, as I said, assuming that string theory is the best candidate for achieving the standard model as a lower dimensional realization. Then I will be using quivers as in the context of higher dimensional quantum field theories to show you how some of the advancements in that field can be used to develop the understanding of the Hilbert series in beyond the standard model setups, which was one of the first points I hinted at when I talked about motivations and roadmaps. So obviously the last section is going to be very much speculative, because I will present most of the results that have been made in higher supersymmetric setups. But of course, we know that the present world has broken supersymmetry. And so to achieve that in mathematical terms, that is very hard. And currently, this is not understood how to be done. What we know are methods to obtain lower supersymmetric setups by dimensional reduction, performing dimensional reduction, and we will see that in a particular example, which is 60 n equals 2 superconformal field theories. So we know how to deal with lower supersymmetry by dimensional reduction, but we don't know how to achieve complete supersymmetry break-in, and with that, the realization of the standard model yet in a complete mathematical formulation. By mathematical, I mean in the categorical sense. So we still don't know what these are. So now we start off with, so this is basically an outline. So now we start with some preliminaries. So this is, as I said, the first part is going to be very pedagogical. So apologies if you already know all this, but things will be more technical as we go on. So just for completeness, this is presented here. So I will first discuss a very mathematical background, which is supposed to be for people that haven't dealt with physics at all up to now. So I will show you how some of the mathematical tools that you already might be familiar with are actually a good bridge to get to particle physics, okay? So especially in light of what we will see later. So some background for the moment will be discussing a little bit about Riemann surfaces, a brief, very brief overview of Riemann surfaces and the sigma model and the nonlinear sigma model and moduli spaces. So why is it so? So this is important because from Riemann surfaces, the sigma model is basically a way of defining how a particle moves on a surface. That particle moving on a surface is basically described in terms of Hamiltonian formalism. And the Hamiltonian is related in physics to the Lagrangian and the action, which in turn are used to define the partition function. So the sigma model is a prototypical example of a scalar field theory. And the nonlinear sigma model can be then in turn used for describing interacting theories. So, and moduli spaces are essential in relating this mathematical part to physics because in string theory, for example, moduli spaces are essentially describing what are the minima in the landscape of the possible vacua that you can achieve by dimensional reduction of the 10-dimensional string theory. So moduli spaces essentially encode the notion of all the fields and interactions that are present in a given vacuum. So this is why they're important here. So we start with Riemann surfaces. So we take a smooth manifold, and for every point in the manifold, there's an associated vector space and the tangent space of it at that point. So there's also an inner product defined on the tangent space, and we can define the length of the curve. To define the length, we need the definition of a Riemann metric, which is defined in this equation. And we introduce a norm. So altogether, the manifold M and the metric give us the definition of the Riemann manifold. Now, we can look at the geodesic structure of a Riemann manifold, and this is described by the so-called Hamilton-Jacobi equations. So the Hamilton-Jacobi equations are essential if you want to find what is the action, because basically it's a derivative of the action plus the Hamiltonian. They give equal to 0. So this is a way of achieving an extremized action. So you can write down the Hamiltonian, if you are in this setup, as a half Gij pi pj, where the p's are nothing but the momenta in the context of physics. And you can define then the conjugate variables, qi dot and pi dot, in this way, using the Hamiltonian formulation. And so you can then rewrite the Lagrangian using these new, this redefinition, the Hamiltonian formulation. Now, the sigma model, as I mentioned, is an example of a field theory that describes a particle that is confined to move in a given manifold. So the manifold could be anything, could be a Riemann manifold, a Lie group, or symmetric group. And if we couple this to a gauge field, which I haven't defined yet, but I will define later on, we get the Landau-Ginzburg model, which is very useful in contexts such as homological mirror symmetry or other mathematical formulations of string theory that maybe we will be able to touch later on in the course. But the simplest example of the Lagrangian density is basically the following. So you write the Lagrangian as a half summing over the indices of Gij, partial derivative of phi, partial derivative of phi j. And this G is a metric tensor that runs over the field space. So this automatically encodes in it the notion, the fact that you assume that all the fields on the field content is completely known. And so more geometrically, each field that we have is a map from the manifold that we start with to the field space, this capital phi. And then we can take a point on the manifold and define the differential at that point and the partial derivative as a consequence of that. So altogether, putting all this together, we can write the action, which is the integral over the manifold of the Lagrangian density that we had before, as a half the integral over the manifold of d phi wedge Hodge dual d phi. So this action is the simplest that you can write down in this context, and you could have, instead of phi, you could have tensors. For example, you could have had if you had a two tensor, this could have been f. In the case of gauge fields, we will see that this is actually the case. Okay. Okay, so the sigma model, we continue. Basically, it's nothing but a non-interacting quantum mechanics. So as I said, this action that we had before is the simplest that you can write down because it's purely kinetic terms. So if you know in physics, the energy is a very important quantity, and the energy is the sum of the kinetic and the potential part. So in this context, this equation is actually encoding only the information of the kinetic part. We still don't have any interaction involved, okay? So that's why I'm talking about non-interacting quantum mechanics. So then, as I also mentioned earlier on, moduli spaces are very important as a bridge in between, pure maths and physics, because especially in the language of algebraic geometry, moduli spaces enable us to find solutions to geometric problems. We will see this more explicitly later on. Now we turn to the nonlinear sigma model. Okay, so we consider Minkowski spacetime, and we denote the field space with this curly f, and with the capital L, the variational one form. So then we take the fields to be m to the n to r, and we can define this kinetic term in this case as a half d phi squared dnx. And we can split the
Can I ask
coordinates in between. Yes?
Yeah, no, I just have a request. Could you go a little bit slower?
Sure, yes, I thought that I was going too slow. I'm very
No, no,
sorry.
no,
Sure,
no.
yes. No,
I mean,
oh,
I don't know.
absolutely.
Maybe there are many experts in the audience. But if you could go back a couple of slides,
Sure, yes. Where? Yeah.
a little bit before that. Yeah. Yeah, no, no.
This
No, the next slide. Yeah.
this one.
Yeah. Yeah. I mean, if you
Yes.
could just go over the notation a little bit.
Sure,
I
yes.
mean,
I'm very sorry. No, please do always ask, because I just, if I don't hear anything, I think everything is fine. So, okay, it's fine for me to explain better.
hmm,
Okay, so
okay.
let's start from the start. Okay, so this little phi, this is the field, one field, a field that I have in my manifold. And this field is a map, okay, that goes from the manifold, the Riemannian manifold I have, to the field space. This is a capital phi, okay, on the right. So basically, the field space is a set where you have many different fields, possibly, okay? So this field belongs to this set, okay? Then I take a point on the manifold, this x in the manifold, and on this point, I can define a differential. So this is what I mean by dx. This is the differential at that point of the field. And this is defined as a map that goes from the tangent space of M at x to the tangent space of the field space at phi x, so the value of the field that I'm looking at that point. Are you okay with this?
Yes, no, I'm fine. That's good. What I was wondering is
Okay.
what happened to the metric in expression 10?
Well, it's encoded in this notation already.
Right. So that wasn't, completely clear to me. Exactly. So
Okay, no, it's because
yeah.
of this Hodge star. Okay, whenever you have this notation, so this notation is always encoding the metric in it. It's already implicit in the notation. You don't need to write it down.
Okay, thanks. Got it.
Okay. Any more questions on this? No. I assume that everything is fine, but please do stop me if something is not clear. Is it okay if I proceed where I was? So I'll say I was here. Okay. Now, so in this case,
Excuse me,
yes,
I have a question. When you put the Hamiltonian and when you introduce the Hamiltonian, you put a GA. There is a G
this one.
with two.
Yes.
Yes, but that G it's not the same that the in the next slides, right?
No, it's not. It's not. It's not. I've
Okay,
been very sloppy here. I've been using, you are completely right. I've been sloppy with the notation. This G, I said it, but maybe I should have stressed it more. This G is a metric in the field space.
oh, thanks.
Are you okay with that?
Yeah, I'm okay.
Okay,
Uh,
thank you.
thanks.
Okay. So let's go back here. Okay, so I was writing down the kinetic part in the Lagrangian, okay, and I can split the time dependent, which I denote with 0 as the index, and the space dependent part. So the difference in the sign here in front of the terms is because I'm assuming a certain choice of the signature of the metric. Okay, so you could have had, if you choose another convention, you would have had the opposite signs in front of the terms. Okay, so this is a matter of convention. Now, the nonlinear sigma model, I'm introducing a potential. So a potential, I introduce this potential with a degree less or equal to 2. So I can write down, for example, this kind of Lagrangian where I have the first one, which would be the kinetic part, and then I have a mass term. Okay, so this is an example of a first example of a Lagrangian density, which is not just the kinetic part. Okay. But then, sorry, I have this toolbar. I have to remove this toolbar. I need to figure out how to do that because it's covering. Okay, so now, so we can look now at theories that are more interesting because this theory where I have just the mass term squared, it's not very interesting. Okay, so we would like to see something that involves like interactions effectively. So we want something which is not just a quadratic potential. We would look, for example, for something like a quartic potential. Now, the reason why we don't look for cubic potentials in this context is because cubic potentials are associated to Hamiltonians that are unbounded from below. So from a quantum mechanical perspective, it's like saying that you can't define the minimum energy of the system. So it's like an unstable configuration. So in physics terms, it's better to have something that has a well-defined minimum in terms of the energy, because that's supposed to provide the ground state that you begin with and on which you can then construct the particle spectrum as excitations of the vacuum. So this is basically the expression that shows how to write down the Lagrangian density in presence of potential. Now I can't, for some reason it doesn't go, slides don't change anymore. Oh, now okay. So now we can write down the energy functional. So the energy functional can be defined now as a sum of the kinetic terms and the potential term. Okay, so these two, the first two are all the kinetic terms in all the directions, time and space, and then the potential. And in this setup, I can define abstractly the space of solutions associated to the fields. Okay, so this is what I call with curly M, and vacuum is the index here. So this space of solutions is my moduli space. When I referred to it before, I said this is the space that encodes all the field content of the theory. So these are actually the vacua that you have in this. So the vacuum configuration is defined in terms of this moduli space. And it's a subset of the space of all static fields of finite energy, which I denote with this curly F En. This is just a standard notation. Now, let's look at a particular example. Okay, let's look at the real scalar field. So for the scalar field, we have a potential, okay, and one usually assumes that the minimum is at some value equals 0 of the potential. Now, this is something very important that you have to bear in mind. So when you talk about interactions that don't involve gravity, you can always shift the potential without actually affecting the physics that you're describing. So you can always redefine the potential such that the minimum is located actually at 0. Just for convenience, when you do calculations, it's easier to deal with. But if you deal with gravity, it's important to bear in mind that it makes a difference whether you're dealing with a minimum in energy that is positive, negative, or 0. So in that case, you can't arbitrarily shift without actually affecting the physics. So in this case, I'm not going to talk about physics involving gravity, so I can always assume that this is true, okay? So I can always shift the potential such that the minimum is at 0. So the solutions, in this case, the moduli space is going to be defined as the potential to the -1, looking at the potential as a map, evaluated at 0 because I'm assuming that to be the minimum of the energy of the system. So for example, if I take the manifold to be x equal r and the minimum to be at 0, the resultant theory is that of a massless real scalar field. So this means basically that I have, sorry, I said something wrong. I didn't mean the manifold. If I describe, if this is, if the points where v is equal to 0 is a line, basically this is going to be the case where I have flat moduli space, which means that they are unlifted. So in this case, the vacuum configuration has a moduli space, which is just the real line. And so this means that the moduli or the fields that I'm describing are basically flat. Okay, so they just have a kinetic term. On the other hand, if you turn on a potential, which is something like m squared over 2 phi squared, which is the mass term that I had in the previous slide, then in this case, the moduli space is going to be a single point where the field is just going to be 0 as a value, because I'm assuming that the potential is 0 in the minimum. So you see that the potential vanishes when phi is 0. Now, for the case of aquatic potential, this is the profile of aquatic potential where you have you have two degenerate vacua. You have two possible configurations. So you have two possible points. You don't just have one. The difference is that, so this potential is just a parabola. So that's why you have just one minimum, and that's why you have phi equals 0. And here you have two minima. So also the corresponding moduli space is going to be two different values of phi minus and phi plus. Now we turn to the case of gauge theories. Okay, so for gauge theories, the simplest case of gauge theory is Maxwell theory. So the difference with respect to the previous case is that now with gauge theory, we add some kind of higher symmetry structure to the physics that we're trying to describe. Okay, so electromagnetism is important because it gives us a notion of charge also, a first notion of charge. You can think of mass as also being a charge, but from the point of view of quantization, maybe it's better to think about the electric charge first. And you know that there's this duality in between the electric and magnetic charges in Maxwell theory. So as we will see later, we will define charge in the second chapter. But just to bear in mind that this is a first case where higher symmetries are involved. So in this case, the data that you need to define the theory is a compact Lie group and a corresponding Lie algebra. Sorry, this is, I should have put this same notation. So this is what I really meant. So I will edit this, but this is actually a math frac G. So, and then a bi-invariant inner product on the Lie algebra. So from this data, you can define the Lagrangian density, and the integral of the Lagrangian is going to be -1/2 Fa wedge Hodge star Fa. So as you can see, this is basically the same that I had in the case of the scalar field, just by replacing the scalar field phi with Fa, where this is the tensor, the Maxwell tensor. So this gives me the energy density, Ea, which is now a half sum over all the mu's less than nu of F mu nu squared, integrated over the spatial coordinates. So in this case, the moduli space is still a point, okay? So now we can combine a pure gauge theory with a sigma model that we had before, both of which are very useful to define for describing quantum field theories. So the data that we need to build the composition of the two is basically a set of all things that we saw before. We have a Lie group, a Lie algebra, a bi-invariant scalar product on the Lie algebra, a Riemann manifold on which the group G acts by isometries, and a potential function. So you see we are gathering all the material that we saw before, all the data. So now the space of fields is now going to be built of two constituents. One is A, which is the Maxwell potential, and phi, which is the scalar field, okay? So basically A, mathematically, is a collection of all principal G bundles on P, and phi is a section of the associated bundle over P times X that goes over M. So basically what I'm doing here, I'm saying that the space configuration is a set of pairs made up of each field that lives in my theory. I could have had more fields, and so in that case, the space of fields would have been an n tuple of all the of a representative of each different field. Okay. So we can look at an equivariant map. It's convenient to look at an equivariant map that sends basically that induces isomorphisms of fields. So basically we can map pairs among them in this case. Okay, so in between a certain pair of principal G bundles and fields to another pair. Now, the Lagrangian density of this composite system is going to be made of we're going to have terms that are related to the kinetic terms in the energy and the potential energy. So the kinetic energy part is going to be, the kinetic terms are going to be these. So you can see there's the F squared term, which comes from the Maxwell side, and the dA squared, which comes from the sigma model, so the scalar field case, and the overall potential that encodes all of them. So this V could in turn be like the sum of different contributions. It doesn't really have to be just one. It can be many terms. So that's why I'm keeping it arbitrary. And from this, I can define the energy density once more. So it's just the sum over the kinetic terms and the potential. Then obviously times d to the d minus 1, which is just the spatial dimensions involved, assuming that capital D is the total space-time dimensions. So once more, so we assume that V has a minimum at 0, and we can look at the solutions with 0 energy. So we can do this because gravity is not involved, okay? So from this, if we look back at the first term was a half Fa squared. So the first term implies that A is flat. So up to equivalence, it is the trivial connection with 0 curvature. And the second term, which is instead 1 over 2 dA squared, which was the kinetic term of the scalar field phi, implies that phi is constant. And this is required for it to be a 0 energy solution, because that's our assumption to begin with. So what we are left with is just the third term. The third term was the one related to the potential. So from the third term and the constraint that we assume the energy to be 0, we get that phi, the scalar field, is a subset. Its values are inside v to the minus 1 at 0. So you can take this as basically being a proof that the moduli space is a subset of v to the minus 1, 0 that I used before, okay? So a trivial connection, we assume that we have a trivial connection. Sorry, if we assume that we have a trivial connection, this has a group of automorphisms that are isomorphic to G. And for vacuum solution, phi must be a constant function with values in v to the minus 1, 0, as we saw before. So this implies that in turn, v to the minus 1 at 0 is inheriting the same symmetry action from the field phi. So this means that the vacuum, the moduli space, can in turn be defined as v to the minus 1, 0, modded out by G. So we're modding out the symmetry that is also acting on v to the minus 1, 0, because it's inherited from the G action on phi. So for the specific case of certain supersymmetry theories, we're going to come back to this because this is crucial for defining, for example, the Higgs branches. We're going to see them in detail in the second part of the course. But bear in mind that this v to the minus 1, 0 is later on going to be related to the moment map. People that are more familiar with algebraic geometry know what this is already, but we're going to see this explicitly in supersymmetric theories and why they are useful. So before getting to, yes, please.
A clarification, just to, again,
Yes.
a bit of notation. I think, I mean, I don't know what the audience is like, but maybe it's not clear to everybody that what v to the minus 1 means. If you could just clarify that,
Well, because
that's a source of confusion.
So v to the minus 1, okay, v to the minus 1. I'm assuming that v is a map, okay? Are you okay with that?
No, I understand it. I'm just saying for the sake of the audience, maybe it might be helpful to clarify that.
So I'm assuming that v is a map, okay? So v to the minus 1 is actually like the inverse.
Right, it's a set of points on which the potential vanishes. It's not the 1 over v, right? Okay,
No, absolutely not. I'm sorry if that was what you might have thought. I never thought it that way, you know, but thank you for pointing it out but I can assure you this is standard notation. It's not my notation. It's something that, thank you for pointing it out. I will say it in some other occasion. I will stress this better, but please, did anybody have this? How many people understood that that was 1 over v instead? I hope nobody, but okay, I'm very sorry if that was what you thought. But of course, no, that what I really meant was the inverse map. Okay, and this is very important to, sometimes, you know, similar notations are used in different contexts, and If you stick to the context, you won't get it wrong. But I agree with you that now that you told me, it might have seemed deceiving. So, okay, so I stress this is an inverse map. Okay, thank you. Any more questions? No, okay. Okay, great. Thank you for the interaction. I really appreciate it anyway. So now we turn to, this is much more discussion, okay? This part is not too heavy in notations, so it's just to give you some, overview of what particle physics is at the moment for people that are not familiar with it, okay? So I've already talked a little bit about fields. I mentioned interactions. So quantum fields are basically mutually interacting entities. This means that they talk to each other, and that's why the interactions come in place. Okay, and they are important to understand because that's where unification. Why unification is needed, okay? Because we have different interactions involved in nature, and we want to understand whether they come from the same source and what that same source is. So quantum field theory is currently the most successful scientific theory to deal with these matters so far. And there's a whole machinery that's been developed over decades, I would say. And the standard model of particle physics is the prototypical example of quantum field theory. It is well known that it's true, but it's not the full theory of fundamental physics. We know that there's physics beyond that, and we need to understand what that is. So to some extent, quantum field theory predicts with great accuracy observational outcomes, and that's why CERN and the LHC and many other accelerators in the world have been developed, because we know that by observing collisions, particle collisions, we can identify possible extensions and where the standard model needs to be developed. So, but it's also very, very important to bear in mind that quantum field theory has been also let me see, explored from the point of view of pure maths, which is my perspective in this topic. So I'm not a particle phenomenologist, but I think that the two fields should talk much more to each other, because they deal with a bottom-up approach, and the maths is much more top-down. But at some point, the two have to agree. So it's great to keep in touch on both sides, to see what are the advancements and whether people can mutually be inspired by results on either side. So, so particle physics so far, as I said, we need to extend the standard model, and this is what is also known as beyond the standard model physics, and they're basically different models that have been developed and are still active area of research to add interactions and particles as possible effective field theories that you could obtain from possibly higher dimensional theories such as string theory. So in a nutshell, this is like one slide, the essence of quantum field theory. But basically, you have a quantum field theory is defined in terms of a Lagrangian density that we saw examples of before. And the Lagrangian density in turn is related to the energy. So, given that, what are the energy levels involved from a quantum mechanical perspective, and what are the possible ground states? But I don't know where you... Okay, was this slide... Did you hear about this slide?
I think you can repeat it. It's okay.
Okay, so I was just mentioning here that essentially the main point in quantum field theory is to determine the Lagrangian density, and from that the action that I have here, because these are the basic parts that then allow us to define the partition function that we will see in the next slide, and from that in turn evaluate amplitudes that are basically the mathematical formulation of scattering processes that happen in colliders. And in turn, they enable to access what are the interactions involved and the particle field content of the theory that is being analyzed. So we saw before some examples of Lagrangian densities, and the action is defined by integrating over all space-time dimensions the Lagrangian density. And for each field that lives in your theory, you can define the you can find the corresponding equations of motion that are basically telling you how that field behaves by performing a variational principle. So it's just you change a little bit, so you add some perturbation to each field, and then you do a variational principle on the field of interest, and you will find the corresponding equation of motion of that field. Okay, so once you have the action, then the action can be used to define the partition function, which is usually denoted by this capital Z. So the definition of the partition function involves a path integral, which in turn is something that is still not known exactly how to be defined in a rigorously mathematical way. For realistic theories like the standard model, we still don't have a mathematical formulation of the path integral. By mathematical, I don't mean integral, I just mean the categorical. We don't have a rigorous categorical definition of this path integral. As we will see later on in this course, there is a rigorous mathematical definition for gauge theories and for sigma models of the path integral, but when involving more intricate situations like the standard model itself, we still don't have that kind of structure. But that's one of the directions where the maths needs to be developed, and where we believe that advancements could be made to understand where to eventually extend that model. So we can think of the partition function as being essentially the calculation of the expectation value of the identity. Why am I saying this? Because when you calculate, when I talk about correlators, like this expression here, number 38, correlators are basically nothing but calculations of scattering amplitudes. So when I talked about amplitudes before, I said these are the setups, the physics setups, where actually observation tells us where the need to extend a theory is or can be seen. So we can think of each one of these observables that I call capital O as being different particles, okay, that scatter with each other, which means I have some number of incoming particles and some number of outgoing particles, and each one of them is going to have a different speed. So with speed, we have a different kinetic energy associated to each particle. So that's what I denote by P here. So I have a collection of these particles. I want to study what the amplitude of that scattering process is. And in terms of the partition function, this is expressed as a path integral over all the fields of these operators, these observables, okay, these are basically the particles, times e to the minus s. So basically what I did, I've put these observables inside this integral, defining the partition function. So that's why I'm saying that the partition function is in turn like the expectation value of the identity, because you can think of one as being just a number placed in here, and you're looking at what the identity looks like. And also, more formally, you could also consider what is the normalized correlation function, in which case you should divide by the partition function, but this is a detail we can skip this for the moment, it's not important. So basically, this is in words what I already said. So amplitudes as I said, they're important to understand scattering processes, and they are the basic building blocks for defining transition amplitudes between different quantum mechanical states. Because if we go back here, basically in this notation, there's a whole world that is hidden. I'm basically assuming that this expectation value is being calculated on the ground state. But I could have also written this in a different way. For example, I could have taken each one of these observables to act, each one of these particles to act on as an operator on the ground state. So this means that if I take an operator and I act on the ground state, I would get an excited state. And that excited state is going to be associated to a correspondent state, which is in one-to-one correspondence with that particular field that I'm looking at that particular value of the energy. So I could have rewritten this as the expectation value of the identity on an excited state, a state that is built by a tensor product of different states at different energies. So that's what I mean when I say that the amplitude is also like a transition amplitude in between, the scattering is like a transition amplitude in between different sets of fields. So basically, if we look at, if we have we can make predictions on the basis of these calculations, we can make predictions of what the observables should be. So we have a certain number of incoming particles. We can predict what are the outgoing with some uncertainty, and we can then eventually measure if those observables actually match the predictions. And if they don't, beyond the error, then it means that we need to develop the theory more. So this is basically a picture of what I meant. So you have some incoming particles on the left, for example, they scatter in this bubble, and then you have outgoing particles that are in different, they could be in different number, and they could be different particles, okay? Now, this is just to give you a flavor of where we will be heading next. Not now, not today, maybe in the last lecture or so, but basically you can reformulate in a much more mathematical way the scattering amplitude by looking at Hilbert series. I will just explain now what is the Hilbert series, and it's basically encoding similar information as the scattering amplitude because it heavily relies on the complete notion of the field content and the symmetries involved in your system. So basically, if you know that, you already know how to write the whole Hilbert series. And implicitly, I should have said, the notion of symmetries is encoded also, of course, in the definition of the partition function, because this is a very shorthand notation. In principle, the partition function is an integral over all the fields, okay? So this phi is not just one field, you have different fields altogether. And according to the symmetries of each field that each field carries, then you would have extra structure to be added to the path integral. So that's why it's a key element. If you know the full symmetry structure, then you also know how to write the path integral. So similarly, same happens for the Hilbert series. Now, Hilbert series have been used a lot, both in the phenomenological setup, for example, in minimally supersymmetric standard model with n equals 1, but at the same time, it's been developed on a completely different spectrum from the point of view of highly supersymmetric theories, such as 5D n equals 1, which we will deal with later on, in studying Higgs branches and Coulomb branches built out of brainwave systems. So it's a top down approach, certainly, but you can see that the formalism is the same essentially, and so this is why this is a promising bridge in between the two sides. Okay, so the Hilbert series is essentially made up of two main parts. One is the Haar measure, this d mu that I have, and the other is the plethistic exponential. So the product here runs over all the gauge groups that I have in my theory. So if I have the standard model, this would be a product of 3 terms, for example, okay? but this is arbitrary. It depends on the theory that you deal with. And you have, for each gauge group, you have a corresponding Haar measure. And for each field, you have a corresponding plethystic exponential. And the plethystic exponential takes a different form according to whether the field that you're dealing with is a boson or a fermion. So the difference in between them is just a spin. So I don't have much time to deal with the explanation of that for the moment, but just take my word. It's basically an intrinsic property. The spin is an intrinsic property of the particles, and you have to think of it as being essential in the sense that bosons obey different statistics with respect to fermions, in the sense that energy levels are filled in a different way. So if you have bosons can fill with no bound any energy level, and that's why that's because a consequence of the fact that they have integer valued spins, and fermions instead obey the exclusion principle, which means that they can only be paired together. So at most you can have two fermions with the same energy level and not more than that. And at the same time, it also implies that they tend to pair up instead of filling, but instead of filling higher energy levels if they are the same particle. Okay, so but this is just it's not very important for what we will be dealing with. I just added these expressions now here for completeness. Okay. So as I said, this is the Hilbert series is important because it already assumes that we know everything about the theory, the symmetries, the particle contents, and so that's why it's important to see if we could relate Hilbert series with different supersymmetries together and how that affects the symmetry structure, because that could tell us how dimensional reductions, for example, could affect the field content or the symmetries involved in our theory. So it's a promising tool to study lower supersymmetric realizations starting from higher supersymmetric ones. Okay, before turning to this part, are there any questions? I hope I have not decoupled.
I have a question.
Yes, yes, please.
Well, it's just that the Hilbert series sounds like a very mathematical construction, and I for one have never seen it before. So could you maybe talk a little bit more about what it is, where it comes from, and so on?
So the Hilbert series it's basically you find it in algebraic geometry, okay? So I didn't really explain it. You shouldn't consider this as the explanation that I will give in this course. I will deal with this much more in detail. We will see examples in probably the third lecture, okay? So I just wanted for the moment to show you that there's a mathematical formulation. As you said, it's a very mathematical construction, but it's something that encodes the same information that you would expect to have from scattering amplitudes. So this is why basically you know that you start from a system that has certain symmetries, and from those symmetries you have associated gauge groups, okay, and those groups are you assume that they tensor together, and you just want to find some invariant. So it's basically the Hilbert series is like an invariant, okay, that you want to calculate, and it gives you the degrees of freedom. In some way, it encodes the degrees of freedom of your theory, and we will see in the case of higher supersymmetric theories that this is a very important tool because it relates under duality theories that are mirror dual to each other. I know that this may seem very abstract for the moment, but if I start going into the details of this, I lose track of what I want to say next. So I would ask you for the moment to just bear in mind that this expression is, as you said, very mathematical, and most importantly, it encodes the same information that the partition function has. This is my main message with this slide, okay?
Yeah, so I mean, it's basically you're calculating the invariant of some quantity over a group.
Yes.
Okay, got it. Thanks.
All the groups of the theory. This is what I mean. Okay, so I don't have just one group involved. I'm assuming this, I'm calculating this over all the groups of the theory. Sorry, I have the alarm test now. I'll just shut this is going to be quite long. So this is the second part, and it's going to be probably a lecture and a half, I think, at least. So it's quantum field theory from category theory. This is, as I mentioned, it's there's a whole Simon's collaboration working on this. They started off 3 years ago, and it's a very promising direction towards achieving effective quantum field theories from high dimensional setups and highly supersymmetric setups as well. So it's basically a mathematical machinery to identify the definition of the partition function and correlation functions from a purely categorical perspective. And this is what I will be reviewing in this part, because I think it's very useful, especially if you come from a mathematical background, to appreciate where the current, the present day understanding is of physics and where to eventually extend it further. So main motivation for this is basically to understand what is a quantum field theory. Presently, we don't have a high categorical structure description of the standard model, as I said, which basically means that we don't know exactly how to generalize integrals, group structures, and algebras in a more abstract way when starting with more physical theories like the standard model and extending them eventually to be embedded in string theory, for example, and to understand where unifying theories, how unifying theories can be best chosen using this criteria. So for those of you who are not familiar with the categories at all, this is just a brief overview of what categories are. So higher categories basically means that they are extensions of groups. So groups are just elements and relations in between them. Categories are an extension of groups. You can think of groupoids as the easiest examples of categories where you don't have higher categorical structures. Higher categories means that you have morphisms in between morphisms. So you have objects, just as in groups. You have modern morphisms that are the relations in between objects. And then you have relations in between relations, which are called two morphisms, and so on. You can build a hierarchy of morphisms. I have this diagram here that shows you can have points. These points are the objects, and the morphisms are the red lines in between them. And then the two morphisms are the blue lines, and so on. You can build a hierarchy that ends up to some n morphism. At some point, obviously, you hit a triviality, which means according to the dimension that you're dealing with, at some point it doesn't really make sense to talk about higher morphisms because they would just be equal to the identity. So it's important to define what this n is in the context that you're dealing with. And this is basically an essential requirement that sometimes you might not have and you might need to look for, okay? So the key point is that they generalize, how categorical structures generalize the notion of groups and algebras. And because of this, they are important to keep track of the field and particle content of a theory. So this is why we will be seeing a particular example, which is the the dimensional reduction of 6D n equals 2 superconformal field theory, which for mathematicians is also known as theory X. So why is this theory so important? It's because it's the highest supersymmetric theory that you can think of. And relying on that, there's a lot of mathematical structure that can be employed to understand what is then to understand how to dimensionally reduce it and have control on those dimensional reductions. So it's a top-down approach, but it's important in model building, as we will see later. So we start from basically, I'm going to do now what I talked about in the previous part, which is sigma models and gauge theories. I'm going to turn to the categorical description of those sigma models and gauge theories, and see how to define the partition function in a categorical language, okay? But this is assuming that I have just one theory, which means, sorry, one field. So I have just one scalar field or just one connection. So it's a case-by-case study, okay? I'm not talking about composite theories in this setup because those are very involved and we presently don't know how to deal with them in this language, okay? So we start from principal bundles and connections. This is a review of some terminology. So we start from the same data that we had before. We have a manifold, a Lie group, and a principal G bundle defined as a manifold on which the Lie group G acts freely with its quotient. So we have an isomorphism, this phi I, that goes from two principal G bundles over M. And this is a smooth diffeomorphism that commutes with the action of G, so with a symmetry that is underlying it, and induces the identity map on M, okay, because they are both principal G bundles over M. So if P is equal to P prime, this automorphism defines a gauge transformation for P. So this is basically the mathematical definition of a gauge transformation. Now, a crucial thing is that of understanding what are the boundary conditions of the fields that live in your theory. The reason why I say this is because the choice of the boundary conditions is associated to the definition of the spectrum of charges. We will see what charges are in mathematical setups, but for the time being, just think of having electric and magnetic charges, just to bear in mind them. And we know that they are quantized, okay? We assume that there's a particular choice of electric and, sorry, if you choose a particular choice of boundary conditions, that choice automatically tells you which charges are electric and which charges are magnetic. Now, they are dual to each other. So this means that if you change the boundary conditions, the change of boundary conditions is going to affect what are the electric charges in your theory, and as a consequence, they're going to change also the corresponding dual magnetic charges. So the spectrum overall is going to change of the theory. So it is important to have a suitable definition of boundary conditions and make sure that you bear them in mind. But most importantly, it's important how to bridge in between different choices of boundary conditions. So to understand the theory in depth, we need to know how these boundary conditions differ from each other, because in turn they give us insights on a richer structure that underlies the whole theory. And this is the starting point of the quantum field theory from category theory perspective. Okay, so we have a certain set of symmetries in the theory, and we assume that they are expressed in terms of some topological defects that act as operators on state spaces. Now, we will see what this means in concrete examples, but basically it tells you that the symmetries can actually be turned into some objects that actually act on the states of your theory, so on the fields of the theory, okay? Now, Friedmore and Telemann were the first to put forward this picture, which is called that of relative field theory. Sorry, not relative. Relative field theories started off as a term that was introduced by Fried and Telemann just after a paper by Witten that dealt with these six-dimensional n=2 superconformal field theories that I mentioned before, because that is an example of a relative field theory. And they also dealt with this description in terms of sigma models and gauge fields. But Friedmore and Telemann developed the so-called symmetry topological field theory, which we will see later. And it's a development of the relative field theory perspective. So the relative field theory already tells us that we have a choice of boundary conditions. So there's a whole category of boundary conditions that we can choose from. So a quantum field theory that we call F is defined as a composition. So the theory that we have, certain quantum field theory that we study, is basically coming from the composition of two parts. One is a relative field theory, this F tilde that I have, and then I have raw. Raw are basically the topological boundary conditions that I implement on the fields that live in the relative theory to obtain a certain spectrum of operators and charges in my absolute theory. So I'm basically going backwards. I'm trying to open the theory and see where it came from. So to understand it intrinsically and see how we can change the boundary conditions to achieve a different spectrum of operators on our resultant theory. So in pictures, what I said is basically this. On the right, I have my absolute theory, F, with a label in raw, which says I'm basically keeping track of the choice of boundary conditions that automatically select the charges that live in my theory. And that choice is nothing but a topological theory on its own that lives on the boundary of a bulk, which is the symmetry topological field theory that is attached to the relative theory F tilde. So as a whole, you can get from the left to the right by compressing the two sides, raw and F tilde, to achieve the absolute theory. So in physics, we usually study just the right-hand side, okay? From the bottom-up approach, we have a given Lagrangian and certain interactions and particle fields. So we know already, we just know this. We just know this side. And we automatically assume that the charge, so not assume, but we have implicitly in the choice, sorry, I'm using the wrong terminology. If we start from a certain Lagrangian and we define the path integral, that path integral is already encoding the choice of the boundary conditions. This is just part of the formalism, okay? So we are automatically assigning a certain spectrum of operators and charges to that theory. But in principle, we want to see how much that can be changed without altering the theory. Or how can we change the theory by altering the boundary conditions? And this is why we are interested to go back to this relative setup, which is instead opening the theory and obtaining three parts from it. One part is the red right-hand side here, F tilde, which is the relative field theory, which means I have the theory I began with, but with open boundary conditions. So I don't have any boundary conditions fixed for the fields. I just know what the fields are. So in some sense, it's not yet what it's not enough to understand particle physics because we are still assuming that we know what the field content is, but we don't know exactly what the charges are. So that's already some kind of, extension of the path integral formulation that you wouldn't have if you just looked at the particle physics side, okay? Then this sigma is a bulk theory. It's a topological theory. And it's usually, we will see very explicitly that this is usually Chern-Simons theory. And the left-hand side are the topological boundary conditions that fix the boundary conditions of the fields. So as a whole, rho and sigma define a pair, and this is called topological data as a whole. Now, more mathematically, okay, sigma, which is the bulk topological field theory, is defined as a map from a Bordism category where capital N is some integer. So this is basically the dimension. N is the dimension of my relative field theory that lives on the boundary. So that will be basically the dimension, the space-time dimensions of the theory I want to study in physics. And the bulk is going to be one dimension higher. So that's why I have a Bordism in n+1 dimensions mapped to some category C, okay, in the bulk. Now, what is this category? We're going to see this very, very explicitly in some examples, but basically this category is a category of topological defects that live in the bulk, and they have different dimensions, and they can interact with each other and intersect and fuse, and those fusion rules are crucial to defining what are the charges in your resultant theory, in the F, okay, in F. Okay, so this is basically saying similar things to what I already said. So to each pair, sigma and rho, I have another pair, F tilde theta, sorry, where F tilde is, yes?
Yeah, no, again, so I mean, I understand that a category is a collection of objects and morphisms.
Yes.
And in this case, what are the objects and what are the morphisms?
It depends on the level. Okay, so when I talk about objects, sorry, I have the alarm again. Okay, so this already said. Okay. Okay, so I was talking about, I didn't say this. So, so when I said before that the topological boundary conditions turn basically a relative quantum field theory into an absolute one. So the relative field theories are models where the fields form a fibration. So the fibration is in this expression 46, you see it's basically you have a fiber and a base, and the fields are going to be these pies that I have here. These are the relative fields, the fibers. Now, okay, so this probably I shouldn't have put this line here because it skipped a few things, but basically the path integral over the base reduces to a sum, and we will see this explicitly afterwards. If you want the theory to become absolute, then you should also require that, or also the fiber, integration over the fiber to get a finite sum even in that case. And that would also would allow you to get the absolute theory. But we will see this in an explicit example. So I would probably suggest to go to some examples first. So let me see this one maybe. Let me go to some examples, maybe it's better. Okay, so let's start from the sigma model. Okay, we start from a pair. Okay, we want to recover the bulk. Okay, because the bulk is basically telling that sigma, that what I call sigma, that bulk is basically a partition function. Okay, so you can think of that bulk as encoding all the information, as I said, the symmetries and the fields that live in your theory. So if you know that, you know the whole theory. So that's a visual way of drawing the partition function. So we want to find a pair for each theory that we study in physics. We want to find a corresponding pair alpha and F. F is the absolute theory and alpha is the bulk. Okay, or I should say it's the pair of bulk plus topological boundary. So alpha is a topological theory, and we assume that it's defined on all manifolds, okay, because we still don't fix the manifold, okay, that's why we're still in the relative setup. And F is some Riemann theory, okay, we are in the sigma model picture now, okay. So we use the knowledge of the sigma model that we defined before, and we try to predict what alpha is. So we try, once we know the theory, F, for a given F, we try to reconstruct the bulk alpha, which means we try to find the partition function of that theory. Now, the relative path integral can be written on a closed d-dimensional manifold as an integral over the relative fields, okay? And with this, Fx, which is our theory, is invariant under the symmetries involved, and is therefore expressed as a function on the equivalence classes. And because of this, we can write it down as a map from H1 xg to the complex numbers. Now, alpha x is the bulk, okay, in my notation. This is the bulk theory, and it's d-dimensional, d+1 dimensional theory. Now, this is in pictures, basically what you could think of as the bundles grouped into isomorphism classes, okay? These are the constituents of the partition function. So to recover the bulk, we need to consider a d-1 dimensional manifold, okay, Y, and the relative canonical quantization of the theory on that submanifold, which is obtained by performing a quantization on the fibers of the map, such that the vector bundle is Fy to Bgy. Now, to recover the bulk, we need to select a representative of the bundle, and in each isomorphism classes, this has to be done. So we take m, little m, to lie inside H1 of Yg, to be the class of G bundle, Q to Y, and then the isomorphism group of gauge transformations. And the equivariant bundle decomposes then into topological vector spaces that are indexed by these pairs. So these are basically nothing but the charges. When I talked about electric and magnetic charges, this is similar to that idea. Okay, I have M and D, and M is inside H1 of Yg, and E is the complex irreducible representation of automorphism groups of M. So now the partition function is this functor that goes from the identity calculated on the manifold of d-1 dimensions to alpha y, which is the bulk. It's the topological theory calculated on y. And this is an object belonging to the linear category of alpha y, leading to the prediction that alpha y is the free vector module with basis pairs m and e. So for example, if I have X to be a one-dimensional theory, say that it's a circle, H1 at a point G has a single element, representing the trivial bundle with automorphism group G. And this implies that alpha calculated at a point defines the category of representations of G. This is the lower dimensional thing that I can think of, okay, in this setup. Now, to build the partition function explicitly, if alpha is a finite two-dimensional gauge theory with some gauge group G, this theory has a trivial Lagrangian. So it implies that the partition function on any closed two-manifold is just a sum over R, all the classes of R mapped to M2, of 1 over the automorphisms of R mapped to M2, where the sum runs over all the weighted countings of the G bundles. To turn this into an absolute theory, so this is still the relative path integral, okay? I'm not specifying the boundary conditions yet. To do that, you need to define, take a subgroup of the original symmetry group that you start with, and you gauge that away. So gauging means that now you need the sum is different. Now the sum runs over all the equivalence classes of the subgroup bundles, P to X. And with this, I also need to take to divide each term by this ZG prime and prime that denotes the automorphism group of a representative of each equivalence class. So this is now this is the path integral for, the partition function for the absolute theory. Okay, so this is now an absolute theory. Now, we can do the same thing for gauge theories, but when we do gauge theories, we need to add some extra symmetry structure into play. So basically, we need to turn all the categorical description that we had for the sigma model, we need to increase the categorical level by 1. So to do that, we need extra structure, mathematical structure. And this is why I added here a short slide on gerbs. So in mathematics, gerbs are used for constructing things like homological algebras and topological structures, and they are analogous to fiber bundles. and they're also very much used in differential topology and cohomology classes. So we need them in the context of gauge theories because we have this data as we had before, the Lie algebra and a covering homomorphism. And we can define the adjoint group. That is basically, we remove G0 from G, where G0 is the kernel. And given a principal G tilde bundle, which is the part with the G removed, with the G0 removed, the obstruction to lift in it to a principal G bundle is measured by a G0 bundle, which is the kernel bundle. And B2G0 denotes the collection of G0 gerbs over X. So B2G0 is a 1 category whose equivalence classes are H2XG0. Then you have H1X of G0, which is the group of equivalence classes of automorphisms between objects, and H0XG0, which is the group of automorphisms of automorphisms. So you see you have an additional structure with respect to the previous case. Previous case, we had just H1. Now you see we have H2, H1, H0. So we have morphisms of morphisms that are involved in this case. That's what I have here, okay? Automorphisms of automorphisms. So this higher structure also gets mapped to the corresponding definition of the relative field and the position function. So the relative field associated to a given gauge theory can be defined as this map, G to X, inside B2G0 as a pair. This is similar to what we had before. We had F tilde theta before. So this theta tilde is just like, the absolute theory that we want. And theta is a map consisting of a G connection and an isomorphism of G0 gerbs. So in an ordinary groupoid, which is like the case before, considering non-trivial categories, there would be no automorphisms between automorphisms. So in that case, we wouldn't have the H0 part, okay? So this is why I was mentioning before that this extra part is needed, this H0 x G0. So now this is mapped to, when you consider the relative partition function, this alpha on M2, we're still looking at a two-dimensional setup, okay? We have basically the relative partition function is going to be given by this ratio. On top you have H2 x G0 and H0 x G0. At the denominator it's H1 x G0. So to turn this into an absolute theory, we need to do the same thing as before. We need to select a subgroup. Oh. Sorry, I have the alarm again. So as I was mentioned, this is the last thing for today. So once more, to get from the relative theory to the absolute theory, so we have in the context of gauge theories, two-dimensional gauge theories, this is the relative description of the partition function for two-dimensional gauge theory. And to turn it into an absolute theory, we need once more to choose a particular subgroup and gauge that subgroup away. Once you've defined that, then you use the same formulation as in the sigma model, and you achieve this final expression, which is the absolute path integral for the case of a two-dimensional gauge theory. So with this, I stop and I'm open to questions. We will continue tomorrow.